Well, in just about every physics class, there's a discussion about apparent weight, weightlessness, and actual weight. And almost every physics book talks about what happens in an elevator. So today I'm in an elevator, and we're going to take a look at what happens to the actual weight of an object and its apparent weight. And we're going to measure it with these two devices here. We have a spring scale, which is pretty much the same thing that you see in any grocery store when you put the peaches and the bananas in there and you weigh the materials. This one's marked in newtons, and it goes from 0 to 20 newtons. And then we have an electronic one right here, which is going to be graphing live while things happen as we go up and down in the elevator. Now, if we take a 1 kilogram mass and we hang it on a scale, spring scale, it's going to register how many newtons. How many newtons is the weight of 1 kilogram? 1 kilogram should weigh mg, 9.8 newtons. And I'm going to hang 1 kilogram on this scale and 1 kilogram on this force sensor. And then I'm going to begin to track the weight using the force sensor over time. So I'm going to begin to let it do that. Okay, so I can see now that it's registering a negative 9.8, and that means down is negative and up is positive in this configuration. And now what I'm going to do is I'm going to turn on the elevator and go up a couple of floors, and let's see what happens. Well, I felt a sensation in my feet. How interesting is that? Well, let's take a look at our data a little bit. And this is when the motion began. So let's zoom in a little bit on that. We can see that we had negative 9.8 pretty steadily here with tiny little fluctuations in the sensor. But right here, the numbers actually got more negative, but they're a higher number. It's negative 10.5 for a while, from almost 19 seconds, 19.2 seconds, all the way up to this spot right here, 20.5. So for this duration of time, it seemed like the kilogram got heavier. Now if we zoom out a little bit, that doesn't seem to be the case. From about here on, from here to here, that is, in these little spaces here, there are some fluctuations, but those fluctuations seem to be tiny. They're 0.2 or less newtons. More of the jostling of the ride than anything else. But right here, boy, you can see it dramatically. When the elevator began to slow down at the third floor, instead of 9.8, we ended up with, what is this coordinate right here? Almost 8.9. So it seemed that the kilogram got lighter. Now, does the kilogram actually get heavier? Does it really get lighter? No. The true weight does not change. But this is what the sensors are feeling, and this is what we call apparent weight. And since we weigh ourselves on devices such as bathroom scales that operate under these principles, it would read differently as we would go up and down inside the elevator. Now, what would be great for you to do is notice this in segments. From here to here, no motion. We were sitting on the first floor. From here to here, we were actually accelerating. From here to here, barring some jostling, we were pretty much centered around the same number we started with. This is constant velocity, no acceleration. And then from here to here, we were slowing down until we got up to the third floor. And once we're at the third floor, sitting there, well, it's pretty much the same except for the rocking of the cart and whatnot. So this is normal weight at 9.8. This is heavier than normal, 10.6. This is normal weight. And this is lighter than usual. Okay, so the purpose of this exercise is not only to notice that it does appear that things seem to lose weight at times while they're going up and down in an elevator, and at other times they seem to gain weight, but that they actually don't gain or lose weight. And if you've learned how to do this in your physics classes so far, you should attempt at each one of these stages, speeding up, slowing down, and going at a constant velocity, you should attempt to do free body diagrams for each one of those segments. That is, speeding up, slowing down, and going at a constant velocity, both going from the first floor up and coming from the top floor down. And when you can do that and understand what's happening at each stage, then you truly understand the nature of apparent weight. Finally, you can ask the question, if the apparent weight can fluctuate by that much, what would happen if you removed the support force altogether? And that's basically the definition of free fall, but the object is not without weight. It is not truly weightless. So when we use the term weightlessness in our class, weightlessness refers to apparent weight, not actual weight. Actual weight is a function of m and g. And g can be affected by distance from the center of the Earth, but it's not going to be affected by the distance we go up and down really in a building very much. So g will not fluctuate, the mass of the object doesn't fluctuate, so the true weight does not fluctuate. All right, see you next time.